Well, hello again, mathletes. Today we're going to be talking about roots and particularly square roots and how to simplify them. Um, this is actually a stepping stone as far as solving quadratics because uh, not everything factors, as we saw in the previous chapter. Um, and quadratic equations that don't factor still have solutions. In fact, all of them have solutions. It's just a matter of being able to find them. And so if they don't factor, it turns out square roots are involved. And so we're going to have to take a look at that here. So let's go ahead and walk through and talk about square roots. Now, what a square root actually is, when I use this symbol, if I look at something like the square root of 9 or the square root of 16 or the square root of 144, what I'm looking for is a number times itself that will give me the radicand. The radicand is the number inside of the root. So I'm looking for a number that when I multiply it by itself, or if I square it, I get the number inside the root. And so it's really working the opposite direction of a square. A square takes and multiplies something by itself, and a square root takes something and asks, what did I multiply by itself? And so here, what did I multiply by itself to get 9? Well, the answer is 3. What did I multiply by itself to get 16? Well, the answer is 4, because 4 times 4 is 16. What do I multiply by itself to get 144? Well, 12 times 12 is 144. And so what it's really doing is just working the backwards direction of squaring. Now, the property that we're going to be using a bit, and we're kind of, you have to realize it gets used in both directions here, is one, if I look at this, two numbers multiplied, two radicals multiplied, one of the things I can do is multiply the two radicands and just leave them under the root, right? But the reverse is true. I can also peel these things apart. If I have a product inside of a root, I can tear that up into two radicals. Okay, now here's the other property, because we will be doing this. We'll be tearing numbers up into individual radicals, but really what we're looking for is are pairs of radicals. And so certain things I want you to notice here. So one, if I take the square root of something and I multiply it by itself, right? Square root of 2 times the square root of 2. I'm going to walk through all the steps the first time, but after that, I think we're going to see there's a pattern here. So 2 times 2 is 4, so that means that this is the square root of 4. And the square root of 4 is 2. And so you notice when I multiplied the square root of 2 times the square root of 2, what I got was 2. And so if I multiply a radical by itself, it kills the radical. And you notice that squaring it is really what it's doing. When I multiply something by itself, I'm actually squaring it. So that ends up holding true for lots of stuff, right? Square root of 3 times square root of 3 is just equal to 3. The square root of 4 times the square root of 4 is equal to 4. The square root of 5 times the square root of 5 is equal to 5. The square root of 507 times the square root of 507 is equal to 507, right? I want you to get past the point where you have to multiply it together and then take its square root. You need to just kind of be reflexive about the fact that anytime you have a pair of roots being multiplied like this, it kills the root and you just end up with the radicand again, right? So in general, if I have the square root of a times the square root of a, what I get is a. Okay, so now we are going to take this and I'm going to scoot this over. Let's just go, oops, that's not what I wanted to do. Let's try that again. There we go. That's what I wanted to do. I want to just scroll that up. And let's go ahead and take a look at something here. So let's say I wanted to find the square root of 12. Now, don't make the mistake of saying it's 144, because that's 12 squared. That's the opposite direction of the square root. So here's what we're going to do. We're going to use that property that allows us to break these up. Now, I know that 12 is 2 times 6. So this is the same thing as the square root of 2 times the square root of 6. And so that means that what I can do is break this up. This is now the square root of 2 times the square root of 6. Now, 6 is 2 times 3. So that means I can break this up as the square root of 2 times the square root of 2 times the square root of 3. Now, we talked about this just previously. In fact, we have part of the example up here still. Anytime I take a root and multiply it by itself, what I get is the radicand. And so when I multiply the square root of 2 times the square root of 2, what I get is 2. And so this ends up being 2 times the square root of 3. Okay, now, it's really a matter of finding these pairs, is really what it is. Once you find those pairs, you can multiply them together, get rid of the radical, and just write things down. Now, there's a little more practical way to do this, because it takes a lot when you're writing a square root over every single number all the way down. And so a lot of the time this gets handled by using a factor tree. And the way a factor tree works is you just start splitting off branches, and at the bottom of each pair of branches needs to be 2 numbers that multiply to give me the number above it. So here, 12 is 2 times 6. And you want to be looking for if any of these numbers are prime. So 2 is prime, so I know that's a dead end. It's not going to split up anymore. 6, however, is not. 6 is 2 times 3. And now we have primes at the bottom of each row, or at the bottom of each branch, I should say. And so just like over here when we looked for a pair of roots, you notice these are the exact same numbers. And so if I just pair things up here right now, I can kind of skip that root step. So I have a pair of 2's here, and I know what that really represents is root 2 times root 2. And so that pair of 2's comes out as a 2. This square root of 3, each one of these is technically still in a root. But this square root of 3 doesn't have a pair to kill the root, so it has to stay in the radical. And so basically it works like this. Once you get everything factored out, you start looking for pairs. If everything that has a pair comes out of the root. Everything that doesn't have a pair stays in the root. Okay, so let's look at another example. So let's make this one a little bit little heftier example. So let's say we want to look at, let's say I have the square root of 216. Now you have to be able to factor it, right? That's the first thing. So there's little things to look for. One, this is even, right? So that means 2 goes in. And you might have to turn to your calculator to see how many times it goes in, but it goes in 108 times. Now 2 is prime, 108 is not because it's even, right? Which means 2 still goes into it. So if I put 2 in there, that's going to give me 54. And so I already have a pair of 2's, but I need to finish breaking down the 54 to make sure I don't have any other pairs. So let's see here. 54 is 9 times 6. Neither of those are prime. 9 is 3 times 3. 6 is 3 times 2. And so now I have all the primes I need. And I notice I have 3 3's and I have 3 2's. And so what I want to do here, in fact, you can almost think of this as a little sorting exercise. Sometimes I do it this way where I write the root first. In fact, let's scoot that over just in case we need a little more room. I'll write the root first, and then anything that has a pair I write on the outside. Anything that doesn't have a pair I write on the inside. So starting off here, I have a pair of 2's. And so what that means, since I have a pair of 2's, I can write a 2 on the outside. Now, looking a little further, I also have a pair of 3's here. Well, a pair of 3's comes out as a single 3. And then looking over my circled things again, the only things I have left are this and this, and neither of them have pairs. And so I'm just going to write those here on the inside and then just multiply out anything that's left. So 2 times 3 is 6 times the square root of 2 times 3, which is also 6. And so my final answer is 6 times the square root of 6. Okay, so here's what I want you to do. I'm going to give you one more. Let's see if we can scoot this up a little bit. Good, I do have room. I'm going to give you one for you guys to work on and see how you do with it. And I would encourage you to go ahead and pause the video once I write this down and see if you can work out the whole thing. And then I'll go ahead and play it and see if we get the same answer. Keep in mind that the factor trees don't have to look exactly the same. It's just the primes have to match. So you should have just as many 2s, just as many 3s, or whatever the primes end up being. So let's see if we can simplify the square root of 500. Okay, so go ahead and pause the video. All right, so you had your chance, and here we go. Now, I'm going to go ahead and work this one out twice just to show that there's more than one way to do this. Perhaps the most obvious way that people would go on this one would be 5 times 100, right? 5 is prime, 100 is not. 100 is 2 times 50. 50 is 2 times 25, and 25 is 5 times 5. All right, so if we're going to simplify this, what we need is we need to figure out what pairs I have. So let's take a look here. See, I have a pair of 5s and I have a pair of 2s. So that means a 5 comes out and a 2 comes out. And then I'm left with this 5 all by his lonesome. Right? So if I multiply all of that out, I end up with 5 times 2 is 10. And then root 5 has nothing to multiply. So this ends up being 10 root 5. Right? And so we've just simplified this. Now, I want to work it out a second time. Yeah, there we go. So let's look at the square root of 500 one more time. Now, before we split it up as 5 times 100, but there's a lot of ways you could split this up, right? I could have done 10 times 50, 2 times 250. Let's see here, 25 times, let's see here, 25 times 20 would work. So there's a whole bunch of things that we could do here. So I'm just going to split it down a different way so we can see how this ends up working. So let's see here. 500 is 2 times 250. And we'll see we end up with the same answer. We end up with the same number of 2s, the same number of 5s at the end on this. And then here, 250 is 2 times 125. Okay, and then 125 is 5 times 25. And then 25 is 5 times 5. So you notice I still have 3 5s and 2 2s. Right? So that hasn't changed. So the groupings end up being the same. So if I'm going to go ahead and sort this guy out, let's see here. I got a pair of 2s. So that puts a 2 out here. I have a pair of 5s. So that puts a 5 out here. And then I have a 5 left over. And so I end up with 10 times the square root of 5. And you notice we did these two problems completely different, but we ended up with the same answer. And so as long as you follow the rules correctly, you'll end up with the same answer each and every time. Okay, now, the next part of this, in fact, I think I'm going to go ahead and just clear off the whole board. Let's see here. The next part of this has to do with what happens when you do things like this. Right? The square root of -4. Now, there's some problems here. If you're going to try to take the square root of a negative, we have this issue. The only way I can get a -4 is a positive times a negative, right? I can't actually multiply a number by itself to get a -4. The two main candidates would be -2 and 2. But negative 2 times negative 2 is equal to positive 4, and positive 2 times positive 2 is equal to positive 4. And so how do we deal with the negatives? Well, we actually use that same property we had before, and we split the negative off of this. So what we can do is look at this as the square root of 4 times the square root of negative 1. Well, the square root of 4 is 2. So this is 2 times the square root of negative 1. Right? And the negative 1 has the same issues as any negative, but it's the smallest one. It's the one piece you can always peel off of this. You can always peel off a square root of negative 1 when you're taking the square root of a negative. So if I had, the square root of negative 25, well, that's equal to the square root of 25 times the square root of negative 1. And so it's 5 times the square root of negative 1. And so you can see pretty much any negative that I'm trying to take a square root of, I'm going to peel that square root of negative 1 off. Well, this started happening often enough where mathematicians, being what they are, gave it a name. And so this square root of negative 1, I'm going to from now on refer to as I. And it's actually a little bit easier to think of it as just a quantity I. So really how this ends up boiling out then is if I'm looking at the square root of a negative, right, I can pop that square root of negative 1 off, no problem. It's actually a lot easier to think of it as just popping its I out, right? If you're taking the square root of negative, pull the I out, and I know it's a bunch of cyclopses now, but you pull the I off, and square root of 16 is 4, and so this ends up being 4i. So, excuse me, whenever we have this I in our answer, anything of the form a times I is an imaginary number. And the word of imaginary is really more unfortunate than anything else. It's an actual number. In fact, most of your cell phones wouldn't work. In fact, all of them wouldn't work if we were not aware of these imaginary numbers. Most of the electronics actually deals with imaginary numbers in the computations. So now when you combine these with a real number, right? Actually, let's go ahead and I'm going to change that to a b just for notations reasons. If I have something that's in the form a plus bi, this is called a complex number. Right? So a plus bi is a complex number. So something like 3 plus 2i, negative 5 minus 7i, 2/3 plus 4/5 I, 3 plus the square root of 2i. These are all complex numbers. And technically, even something that looks like this, 2i, even though it is a pure imaginary number, it is considered complex because you can write it 0 plus 2i, right? So 0 is your real number and 2i is your imaginary number. Okay, so we're not going to be dealing with too much of these directly as far as the computation goes, but it turns out that our solutions as far as quadratics go are going to show up in this form. Some of them will. So we need to be able to play with these things a little bit. So let's see here. Let's go ahead and scoot this up here. So let's go ahead and try a couple of these. Let's say I wanted to take the square root of negative 98. Okay, so first things first, let's pop its I out. Right, so it's the square root of 98 times I. So now all that's left for me to do is simplify the square root of 98. So 98 is 2 times 49, and 2's prime. 49 is 7 times 7. Both of those are prime. And that's the end of the line here. So I'm going to simplify the root. I have a pair of 7s, so that means that's on the outside. 2's on its lonesome, and the I just comes back in. Right? And be careful in your notation to make sure that it's clear that the I is not inside the root. The way your book organizes it, they put the I right there after the root, and I think that's dangerous because it makes it look like the I is in the root. So alternate notations, a lot of the time you will see the I written before the root. So you'll see things like this answer, for example, would be 7I root 2. And that's actually a little more standard way to write it, although um, it's also pretty common to write it this way. So both of these are the exact same answer, right? This is the form that your book is using, just so you're aware of which one we're talking about. But I may slip as we go through here and use this notation because that's the one I grew up with. So it's real easy to go back and forth between the two things. Now, looking at the next one, in fact, you should probably pause when I write this down and see what you can come up with on your own. So let's see what you can do with the square root of -60. Go ahead and pause it. Okay, you've had your chance. Now let's take a look. Let's see here. I have a negative in there, so that means I need to pop its I out. And then 60 needs to be broken down. So that's what? 6 times 10, 2 times 3, those are prime. And then 2 times 5, those are prime. Now, I have a pair of 2's. So that means the 2's can come out. I have 2 on the outside. 3 times 5 on the inside, so that's 15. And it's times I. Right? And so I end up with 2 root 15I is what I end up with. And this would be your final answer. Okay. So that's pretty much the end of what I wanted to cover today. So yeah, that's the last of the examples. So keep your wits and your pencils sharp, and I will see you guys next time.